Hello and welcome back to High Peak Education. I would like to perform another sample calculation where this time we are looking for the force per unit length between two current carrying wires, and we'll talk about the directions of the forces but then also the magnitudes of the forces. So an appliance cord consists of two wires, one carrying current to the appliance and the other returning current to the outlet. A. Is the force attractive or repulsive? B. If 5.00 amperes is supplied to the appliance and the wires in the cord are separated by 3.00 millimeters, what is the force per unit length between the wires in the cord? C. If the wires have a mass per unit length of 5 grams per meter, is this force significant enough to affect the wires? Okay, so let's start this problem. First, let's just write down our knowns, okay, and then we'll go into the various parts. So an appliance cord consists of two wires. So there's one wire here that goes to the device, and then one wire here that comes back from the device. Now, by the way, these wires are such that the current goes in opposite directions. So the current goes to the device, and then the other way it comes back from the device. And by the way, this is how most electrical appliances work. When you look at your plugs that you plug into an outlet, current goes into the device and then back out of the device. Hence why you have two prongs. Okay, so that's basically how it works. Now, the current that goes this way, let's call this I forward, and this is I back, is going to produce a magnetic field from the I back that, based on right-hand rule 3, is going to be into the page here. So these are all magnetic field vectors here into the page. So these are all magnetic field vectors that are into the page. So if it's I cross B, the magnetic force should be upward. So this should be the direction of the magnetic force. So it should be like so, upward. Now, by the way, it'll actually end up being downward for the other one. Now, how do I know that? Well, that's because I have a lot of experience with this, but also you can work out for yourself that the current that's running to the right, the forward, by right-hand rule 3, the fingers point into the page, and so this is again into the page. Magnetic field. So these are both B's, and then I cross B is F sub B is down. So we should actually be able to answer part A pretty much immediately. Is the force attractive or repulsive? And it is going to be repulsive. Okay? And you may ask the question like, is this always going to be the case? Yes. So if wires are moving parallel, they attract. If they're moving anti-parallel in straight opposite directions, they repel each other. Okay? Now B, let's write down our knowns. So the current is 5.00 amperes, and that's I1, I forward, and I back. And we know that they're separated by 3 millimeters. So that's typically the quantity A. So the quantity A is 3.00, and we want this in meters, so that's times 10 to the minus 3 meters to get that in SI units. So we want to know the force per unit length on the wires. So this is going to be part B. And then part C, we want to know if we have a mass per unit length. Now, by the way, mass per unit length is sometimes the symbol mu. This is not magnetic dipole moment. This is also not coefficient of friction. This is mass per unit length. And it's 5 grams per meter, but I want this in SI units. So if I have grams downstairs, kilograms upstairs, there's 1,000 grams in a kilogram. So this would be 5 times 10 to the minus 3 grams per meter. Or sorry, kilograms per meter. Okay. And then we want to know, is the force significant enough on the wires? So what's the F, or the acceleration, like? Okay. So we'll get back to that in part C. But for now, let's write down the equation for force per unit length. So force per unit length between two current-carrying wires should be mu naught times I1 times I2, but in this case it's I forward times I back times I back, all divided by 2 pi times A. And I think we have all the numbers, we can put everything in. So let's put the values in. So this should be mu naught is 4 pi times 10 to the minus 7th Tesla meters per ampere times 5.00 amperes times 5.00 amperes, they're both the same magnitude, over 2 pi times A, and A is 3.00 times 10 to the minus 3 meters. Okay, now notice, by the way, before we even go to the calculator, I think these pi's will cancel, and we can make this 2 and this a 2. And then this is the same thing as 5 squared. So that's not so bad. So let's now go to the calculator. I'll move the calculator over here so we can see it a little better. Let's go on and clear. So let's do alpha F1 to get a stack, numerator over denominator. So let's do 2 times 10 to the minus 7th times 5 squared, and we're going to divide that by 3 times 10 to the minus 3. Okay, and then so let's write this down. This is going to be about 1.67 times 10 to the minus 3. So this is going to be approximately 1.67 times 10 to the minus 3. That's going to be newtons per meter. So this is the force per unit length. Okay, that takes care of part B. Now part C. Now we want to know, if we have the force per unit length, how significant is this force? Well, we might want to calculate the acceleration. So acceleration is usually force divided by mass. Remember that from Physics 1. And by the way, let's assume these forces are the only forces, in other words, the net forces. But in our case, we only have force per unit length. But that's okay, because here we have mu, which is the mass per unit length, which again is mass per unit length. So I think the per length business will go away if we just divide force per unit length by mass per unit length. So let's do this calculation. Force per unit length was 1.67 times 10 to the minus 3 newtons per meter. And we'll divide that by 5 times 10 to the minus 3, and that's kilograms per meter. Now these 10 to the minus 3s would just go away. So I think in the calculator we get something pretty nice. We just have to do 1.67 divided by 5. Now we get a pretty small number. It's 0.334. Okay, so this is equal to 0.334 meters per second squared. Sorry, that's a second squared. Okay. All right. Now with this answer, notice that, is this significant enough to affect the wires? We would say somewhat. Now think about this. An acceleration like that is not zero, but it's not very large. But notice that these wires have to be insulated, otherwise they're going to repel from each other. So part of the reason the wires are tied in to that insulation in the cord is because otherwise they would repel from each other. And typically when you look at a wire to a electronic device, to a and that comes from a wall outlet. You'll see that those wires are close to each other just for spacing's sake and because of where the current comes from. Okay, so thank you very much for your attention. Please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. Please share it with your social network. Please feel free to comment, and thank you for watching High Peak Education. I will see you in the next video.